Hello everybody, welcome back to my channel. This is Introduction to Software Engineering Part 6, where we'll be covering beginner friendly explanation for formal notations for requirements, which is including why formal notations, math notations for requirements, decision tables and trees, ER diagrams, state oriented notations, axiomatic specification, algebraic specification, regex and operational semantics. We'll try not to overcomplex it and try to make it easy to understand. So first of all, why do we need formal notations? Thing is, sometimes plain English is just not enough to describe tricky decision making logic. Suppose imagine writing a recipe as one giant paragraph. Add sugar, but if you're using brown sugar, useless unless it's a humid day, in which case add a bit more flour. Except if you're baking at high altitude. There's like so many. If you add sugar, but if it's this kind of sugar, do that. But if it's humid, then do that. But if you're adding flour, then do that. There's so many cases and conditions. All is in a paragraph. By third exception, everyone's lost is absolutely. So a recipe card with a clear table of ingredients and clear steps is much easier to follow and much easier to check that nothing was forgotten. So software logic has exactly the same problem, just with far higher stakes. So what is the problem with plain text descriptions, you may ask? Long paragraphs are hard to interpret consistently, easy to accidentally miss a condition or combination, hard to verify that the description is even correct. Different readers may understand the same sentence differently. This gets especially messy in steps like loan approvals, membership management, online payments, where many conditions interact at once. The fix, structured and mathematical tools, some of them here are decision tables and trees, we'll be talking about that as well, which organize conditions and outcomes. Next, ER diagrams, which organize what data looks like and connects to what. State diagrams organize how behavior changes over time. Precise math statements pin down exact rules instead of vague wording. The account should never really go negative except in special cases versus simply writing balance is greater than or equal to 0. The second version leaves zero room for confusion. Balance should be greater than or equal to 0. Means balance can be 0 but can be never be negative and should always be, the balance should always be greater than 0. Clearly saying instead of all this much sentence. This is a very small example. We're talking about software projects. There are obviously much more bigger paragraphs and sentences you're going to deal with. So that's why this is a better replacement, a better way to express the idea. So let's give a quick answer. Why do engineers prefer structured tools like tables and diagrams, like how we saw there, over long paragraphs or complex logic? Very simple, to make it much easier to check that every possible case has been covered and reduce misunderstanding. Let's come to the next part, which is mathematical notation for requirements. So 3 small mathematical tools engineers use to pin down relationships and constraints with total precision. Relation notation representing data as tables. A simple way to describe data as a table written as R. In that you're writing A1, A2 until AN, followed by its column. Basically relation for the relation's name followed by its column. Example: student, registration number, name, age. A table called student, what does it say? When I'm writing R and then here I'm writing A1, A2, A and A3 until so on up to AN, what does it mean? A table is called as R and its column, this is row, this is column. So a table called as student is having 3 columns: registration number, age, name. This is what they're trying to say. Now what are implicit equations? Most equations you know are explicit, solved for one variable like y equals to 2x. An implicit equation instead just states a relationship or constraint without solving for anything. Explicit equation is solving using variables, one variable. Implicit equations, they don't solve anything, they just give a function or a constraint, okay, without solving for anything. Example: a circle is written as y equals to, all that is not written. It's written as x square plus y square minus r square equals 0. We have seen this formula, x square plus y square equals to r square, that only. A rule that x and y must together this should satisfy this condition. In software, a database rule like balance greater than equal to 0 is exactly this kind of a constraint. Now let's see recurrence relations. A formula where each term is defined using earlier terms of the same sequence instead of being calculated directly. Fibonacci series. We have all heard this, right? F of n is f of n minus 1 plus f of n minus 2. So base case f of 0. F of 0 is equal to 0, f of 1 equals to 1. So each number is just sum of the previous two numbers behind it. Widely used in algorithms. Suppose if I want f of 3, Fibonacci of 3 will be f of 2 plus f of 1. But do I know f of 2? So no, f of 2 is f of 1 plus f of 0. Do I know f of 1? No. So f of 1 I know is 1. So this one I'm going to put here. And f of 0 I know is 0. So that's going to be 1. This one I'm going to put over here. 1 plus f of 1. F of 1 is 1. That's giving me 2. So on. We're using previous conditions. What we get over here, that we're using here. What we're getting over here, that we're using here. That's what is recurrence relation, using what we get earlier in the next step. Why these matter for requirements? So instead of writing the balance should always say reasonable, you're writing balance greater than or equal to 0. A rule so precise that a computer or a very little-minded classmate couldn't possibly misread. That's the entire point of mathematical notation in SRS. Zero room for wait. What did you mean by that? There is no room for confusion. Very clearly, very straightforwardly you are mentioning using mathematical tool. What makes a recurrence relation different from a regular formula? Each term is defined in terms of earlier terms in the same sequence. A recurrence relation builds each new value from previous one, like f of n depending on f of n minus 1, f of n minus 2 in case of Fibonacci series, rather than computing directly from scratch. Directly from scratch is for regular equations, regular formula. Coming to the next topic, which is decision tables and decision trees. So there's two ways to map out every possible combination of conditions and the actions they lead to. Combination of conditions and the actions they lead to. Suppose think of choosing an outfit based on the weather. If it's raining and cold, wear a raincoat and a sweater. If it's raining and warm, just the raincoat is enough because you don't protect from the rain. You could write this as a sentence, but a simple table listing every weather combination next to the right of outfit is much cleaner and instantly reveals if you forgot a case like snow. Okay, idea you understood. Now this you understand, no, that's secondary. Idea you understood. Why are we using tables and decision trees? Clearly it's mentioning what and all combinations are there, so we don't even by chance miss out any condition or combination which is possible. That's the main role of these. So decision table, a grid that lists every combination of conditions as columns mapped to the correct action. Nothing gets left. Decision table, okay? It's a grid. Look, what is happening? If it's a valid user and password is correct and active around, then login is okay. If the valid user is yes and the password is also correct but it's not an active user, then show error. If the user is valid but the password is wrong, then there is no question if the account is active or not, error. If the user itself is not valid, then again also error. Did you understand how many combinations are there? What all actions can be taken based on that? Okay. It's best for many conditions, business rules guaranteeing full coverage. That was about decision tables. Very simply we understood. Coming to a decision tree. A flowchart style diagram showing the order in which questions get asked, branching towards a final outcome. If it's a valid user, then yes. If it's a valid user, yes. Correct password, yes. Account active, yes. Then login success. If it's not a valid user itself, then no. Show error. So it's best for visualizing step-by-step flow, smaller sets of conditions, and then we can use this. Now what is a table tree? What we saw now, let's compare it. The shape of it is a grid matrix. Here it's a branching diagram. Again, if this is here a no comes, then also error. It's a branching diagram, okay. Logic state is exhaustive, all at once. You can see everything at once. Here, sequential, one by one, step by step, yes, step by step. Scales to many conditions, yes. It gets kind of messy, okay. So there's also the event table, a close cousin that lists events, conditions and system responses in rows instead of columns, usually describing how a system reacts to different triggers. Okay, that's one thing. So let's answer a question. Which technique is better when you have many conditions because it's guaranteed to never miss a combination? We all know it's the decision table. Let's go to the next topic, which is ER diagrams or entity relationship. This is a picture that maps out what data a system needs to store and how each piece connects to the other. What data a system needs to store, how is it connecting to the other pieces? So let's use the analogy of, think of a library's card catalog. There are students, there are books, and there's a fact that a student borrows a book. Each of these is a separate idea, but they're all connected. An ER diagram is simply a picture of exactly this, the things in a system and how they relate. So entity is given by a rectangle. Entity is given by a rectangle. A real world thing. Example: student, book, department. All of that comes under entity. Attribute, a property of an entity. Name, age, roll number. All of this is a property of a student. For example, relationship. Diamond, how two entities connect. Enrolls in. Okay. Cardinality, how many connect to how many. 1 to 1, 1 to 1. Person passport relation is 1 to 1. One person can have one passport. 1 to many. Department employees, one department can have many employees. Many to many. Student courses, many students can apply to many courses. Many students take many courses. Okay. Here they have given the student enrolls in course. Here student is one entity, course is another entity. I think this should have been a diamond if I'm not wrong. The enrolls in is a relationship. How entities connect. Okay. One department can have many employees. Yes, that's 1 to many. But each employee belongs to one department. Each employee, what are they trying to say? One department is there and there are many employees. But each of these employees belong to one department. So what is it? It is 1 to many. I hope you have understood this thing. Entity is rectangle and attribute is an oval and relationship is a diamond according to this. Okay. Hope you have understood. It was not very complex. Simple to understand hopefully. Next come to state oriented notations. For modeling systems whose behavior depends on what has already happened, not just the current input. Think of a traffic light. Red, green, yellow, again red. So the light's next move doesn't depend on timer. It depends on which color is currently showing. The current condition is exactly what engineers call a state. And this notation is how we map out every state a system can be in and what moves it from to the next. So state is what a condition that the system is currently in, idle or processing event, something that happens and triggers a change. Transition is the actual move from one state to another. Action is what the system does during that move. Very simple, straightforward works itself. Coming to state transition diagram. States drawn as circles, arrows shown as transitions, and each arrow is labeled with the event that is causing it. This is one state, this is one state, this is one state. This is transitioning from idle to processing. This is after processing is done, it is transitioning to completed. Okay, and the state it is in, it's an idle state, processing state, completed state. An order processing system moving through its life cycle, example that is. Finite state machines, a limited set of states. A system that can only ever be in one of a fixed limited number of states is called as a finite state machine. This makes its entire behavior easy to map out completely. Finite state machine means what? Basically it is having limited number of states, so we can easily complete its life cycle series. Suppose for traffic light, what is it? Red, green, yellow, again red. For tracking, order is placed, order is shipped, order is delivered. For vending machine, waiting, coin inserted, dispensing. That's it. So why this matters? State diagrams make it easy to spot mistakes, missing states or transitions before the system is even built. Okay, obviously if you imagine you have forgotten the shipped part here, placed the delivered, then something is missing. The whole shift, what you're learning right now is all something which is happening. Look at the heading first of all, look at the heading. formal notations for requirements. We are still in the requirement stage. We haven't built anything yet. This is all which is happening while building the requirements. Remember, requirement setting, the SRS document which I have covered in the previous video. If you haven't watched, check it out. That's a major foundation. Without listing the requirements properly, without confirming what and all is happening, things will go haphazardly wrong in the later stages. Especially if caught in the towards the last stage, then it's a even bigger mess. So this is a very important. You might be thinking, for one requirement document, why are we doing so much? Because that's the foundation. In a state transition diagram, what does an arrow between two states actually represent? It represents, it's already given here, a transition, the system moving from one state to another triggered by some event. Let's come to axiomatic specification now. A mathematical way to describe exactly what a function promises to do before and after it runs. Think of a vending machine's promise. If you insert enough money and pick a valid item, this is the promise before, then the machine will dispense the item and give correct change. That's the promise after. If you didn't insert enough money in the first place, the machine will not guarantee you or promise you anything. Okay. So there are two halves of the promises. One is precondition. What must be true before the function is allowed to run? It's the caller's responsibility to ensure this. You're going to call the function, right? Before you call the function, you should ensure that that much condition is true so that the output will come. That is your duty to ensure. Post condition. What the function guarantees will be true after it finishes running, as long as the precondition was met. Let's take an example. It might be slightly confusing, so much words is there. Simple example, to withdraw an amount. Precondition. If the amount in your account, the amount which you have in your account is less than or equal to, even if it's equal to the account balance, if the amount which you want to withdraw, is less, suppose simply I'll tell you, you have 1000 rupees in your bank, you want to withdraw 500 rupees. This is less than or equal to 1000 rupees. So after withdrawing, you will have post condition, that is 1000 minus 500, you will get 500. This is post condition. This is precondition. What is the precondition? The amount which you are about to withdraw should be less than or equal to the amount in your account. If this condition is met, then the post condition, which is to give away the cash, or which is to give the balance amount, or give the amount which you have asked for, that will be done. This is post condition. This is precondition. Simple. The whole triple, that is precondition. C, P, C and Q is there. What is it saying? The whole idea is offered in one compact form. This precondition, post condition, whatever that is. Precondition must be true before, post condition guaranteed true after. The program of function itself is this. In plain words, if P is true and we run C, then Q will be true afterward. Okay, what happens if the precondition isn't met at all? It will not. Okay, let's see. If someone calls withdraw amount with an amount bigger than the balance, its precondition is broken. The specification simply makes no promises at all about what happens next. The function's behavior is undefined and it's considered the caller's mistake, not a bug in the function. This is the foundation of whole logic used to formally program behave correctly, especially in safety critical software like aviation and medical system. Okay. So let's answer a question. If a function's precondition is false when it's called, what does the axiomatic specification say happen? What we're studying is the axiomatic specification. It says the function's behavior is undefined or not guaranteed. It's the caller's responsibility for not meeting the precondition. The post condition is only guaranteed when the precondition holds. Holds true. If it doesn't, the specification simply makes no claims. The caller broke the contract. That's it. Next, let's come to the next topic, which is algebraic specification. Describing what a data type can do using nothing but equations. No actual code is required here. Think of describing a stack of plates using only rules. If you push a plate onto the stack and immediately pop it off, you get back the exact same plate you pushed. Correct? That one simple rule captures the entire meaning of a stack without writing a single line of code. This is exactly what algebraic specification does for data type. So there's 4 sections here. One is types. What data types are involved? Point, integer, or length. Syntax. Each operation's inputs and outputs. Equations. The actual rules defining behavior. Exceptions. What happens in error cases. So let's see a point data type. Okay. A point needs 4 operations. Okay. First, create. That is make a point from xy. Xcord, ycord. Read back the coordinates and is equal. Compare 2 points. Okay. Create is make a point. Xcord, ycord is to return what, read back the coordinates, whatever is there, and is equal is comparing 2 points. So create, what is it doing? Syntax to from input to output is integer into integer will give point. X coordination from point to integer is equal point and point is giving you boolean. The equation, this is where the real meaning lives. X chord create x comma y x, y chord create x comma y y. In plain words, if you create a point from x and y, then ask for its x coordinate back and you exactly get x. That's the entire meaning of create and x chord defined with 0 code. Might be slightly confusing, don't get overwhelmed, let's move on. So algebraic specifications must also be complete. That is, every valid expression can be simplified using the equation and reach the same final answer no matter which order the equations are applied in. This consistency is what makes them trustworthy. So in algebraic specification, what do the equations actually define? It defines the exact meaning and behavior we saw here, right, of each operation using pure math, no implementation detail. Coming to the last topic of today, that is regular expressions and operational semantics. One tool for spotting text patterns and one will describe our system's behavior as it actually runs. A regular expression, which is often regular expression short form is regx, okay, is a compact notation for describing a pattern that text should match instead of listing out every possible valid value one by one. Think of a bouncers rule at a club. Bouncers, you know, right? So instead of a guest list naming every allowed outfit, the rule might be must wear closed-toe shoes. Regex works the same way. It's a rule describing the shape of a valid input, like must be exactly 10 digits for a phone number. So it's not going to list naming every. It's not going to say this kind of shoes or this kind of shoes. It's not going to say all of that. It's just going to say must wear closed-toe shoes. Now there are many kinds of closed-toe shoes. So it's not going to list all of them. It's instead going to say what kind of input it wants. As much as it's going to say. It's not going to say what it doesn't want, what not, all kinds of different kinds of things. It's not going to say that. It's just going to say describing the shape of a valid input. That's it. Form validation, email, phone number, searching through log files, compiler design, pulling specific data out of text. So operational semantics is describing how a system actually runs. How is it actually running? While algebraic specification describes what a system should do, algebraic will describe what. Operation will say how, step by step during execution, especially useful when multiple things can happen at once. Linear semantics is what in the name itself is there, sequence of steps one by one. Treats a computation as one sequence of steps. If two things happen together, it just picks up the order A, B or B, A. Next, branching semantics draws every possible choice as branching diagram. One state can lead to several different stages. So one state is coming and this can lead to further states and this can lead to, so branching this is. Next, maximally parallel semantics assumes everything that can happen at once does happen at once fully simultaneous. Parallel means what? It's happening simultaneously. Partial order semantics only tracks which events must happen before the other. If there's no required order, they're free to happen concurrently. Okay. Next, the connection. Operational semantics describe a system state and how they change through actions. This maps directly onto algebraic specifications idea of sorts, that is states, and operations, that is actions, which is why the two topics are often taught together. We saw, right, states, actions. This part. States, action, and this is kind of related as we saw, because algebraic one second. Algebra specification and this operations, they kind of relate to each other. operational semantics model assumes every possible actions happens at exactly the same time. Exactly the same time it has to happen parallelly. So maximally parallel semantics. So today we've covered quite much. Very simple, though there were many mathematical concepts. We have tried not to break our heads and make it very simple and beginner friendly to understand. First, what it is. Our main goal in the series is to understand what is it. We're not really digging deep enough as of now, but yeah, I think it's good to understand the basics of whatever it is. So why do we need formal notation? Let's answer a few questions. A basic recap of each of the 8 topics we have covered. Why formal notations? Balance greater than 0 pizza vague sentence because it is precise. Don't say shorter. It can be longer also. This is a very simple example. It can be longer, but it's precise. Math notations. F of n is f of n minus 1 plus f of n minus 2 is an example of a recurrence relation. We are using what we have got from before, right? Next, decision tables and trees which show the order conditions are checked in. Order. When order is coming, what is going to happen? Trees is going to matter. Next, a diamond shape in an ER diagram represents the relationship. Next, state-oriented notations. A fixed limited number of states is called as a fixed, so finite. Next, axiomatic specification. P, what does Q represent? Post condition. X coordinate y coordinate equals 6 is found in which section? Equation. Regex and operational semantics. Which model runs every enabled action at the same time? Maximum parallel. Okay. So as far as I have been answering, I was able to answer all of them. So if you also done that, congratulations. If not, no worries. Do not stress yourself. It's okay. Take your time and try to understand. So thank you so much for watching. I hope it has helped you. The notes are also wonderfully designed by the artificial intelligence which we have now. So thank you so much for watching. See you in the next one. Until then, bye bye.